Okay, so this is section 15.5, part A. Definitely be a couple, maybe 3 videos. We'll see how this goes. But 15.5 is really going to start into the applications of our double integrals. Um, the first part of this is actually going to be pretty much just algebraic. It's kind of an algebraic physics type of lesson here. We will get into the calculus portion of it towards the end, probably in the second video. So the first thing we're going to talk about is we're going to figure out, first of all, how to be able to compute mass, electric charge, center of mass, and something called moments of inertia. And we're going to talk about the concepts of these things again in algebraic terms first, and then we're going to get into the calculus of it. So let's go ahead and jump right into what some of this stuff is. Let's talk about the moment and the center of mass. So you're going to have this surface, whatever this surface looks like in general. So we're going to have some kind of a surface, whatever that is. And the idea of a center of mass is that I can take this thing, and for lack of drawing it any kind of better than what I am right here, that thing right there, I'm going to be able to balance that mass upon the very point at the top of this thing. So if you can kind of think of this mass sitting right on top of this three-dimensional mass is sitting right at the very tip of that thing. Well, this thing right here, because it's something that I can actually balance the mass on, is what's called a fulcrum. And that's literally what the fulcrum does, is it allows you to balance the mass upon that one specific point. And there is a point, again, assuming that there's nothing else acting on this, that something would balance on. So really the idea is that you would have some kind of a distance of this mass from left to right, then your fulcrum would be right there maybe, and we don't know where it is exactly, but it's just someplace on the mass. And then you're also going to have a distance from the top, and I say top to bottom, but more like back to front. Again, think of this as being a three-dimensional mass of some kind, but then your fulcrum is going to hit maybe right there. So it's got kind of an X and a Y coordinate to it. So let's talk about it first of all in one dimension, because I think that'll be easier to start with. So in 1D, in one dimension, basically you've got some kind of a linear piece of whatever this is. Again, something that you're trying to balance. And at one end, you've got a mass. We'll call this one mass 2 since it's on the right. On the other end, you'll have a mass. We'll call that one mass 1. Well, again, there is some place, depending on what these masses are, assuming they're not the same. If they're the same, it's going to be right in the center. That should usually make sense. But assuming that they're not the same, you're going to have something right around, wherever it is, that you're going to be able to balance this mass. You can almost think of it as, I guess for the lack of a better thing, because I don't even know if these things exist much anymore. You can almost think of it as I think they call them a teeter-totter now, or seesaw, or whatever they call it, which is equally balanced, usually left to right, right in the center. But you know that if you've got one person, or like like we did when we were kids, put 3 people on one end versus one person on the other end, the one with the heavier mass is going to be the one that's going to go down. Well, if you were to move the people with the heavier mass closer to the fulcrum, closer to the center, then you could get more of a balancing point. And, we did it as kids, just didn't realize that's what we were doing. But I don't know if they still do that stuff anymore. But the general idea is there is a total distance from end to end. But to the fulcrum, or to that center right there, you have 2 different distances. That would represent distance 1, that would represent distance 2. And the idea is this. This will balance if and only if And you might see that written like this, IFF. That's a short term for if and only if. Excuse me. Mass 1 divided by mass 2 is equivalent to distance 2 divided by distance 1. So the ratio of the masses is inversely proportional to the distances, to the ratio of the distances. So mass is inversely proportional to distance. Okay, if it was directly proportional, then the D1 would have been on top of the D2, with the M1 being on top of the M2, but it's not. Or another way you could think about this, if you were basically just to do a little cross multiplication, you would get that mass 1 times distance 1 is going to equal mass 2 times distance 2. This whole concept is what is known as the law of the lever, or lever, however you say it. And I think there was a really famous mathematician or philosophy, this could have been something, I don't remember who said it. I'm going to get it wrong if I say, it could have been Socrates or something like that. But anyway, whoever said it said, give me a lever long enough and I can move the earth. So if you have a lever which is long enough, I guess sturdy enough, then you could technically move the earth or move something of large mass. But the lever would have to be quite long, obviously, for that to happen. So, just in general, the concept might be something like this. Here you've got your, basically your teeter-totter idea or something like that. You've got your fulcrum right there, and maybe, not drawn to scale, this is an 8-meter distance right here, and that's a 2-meter distance right here. And I tell you that you've got 126 pounds over here. If you know those pieces of information, you could figure out how many pounds you would have to put on the other end of this to balance it. That's the general concept. All right, so you're going to see something interesting as we go through this. There's really nothing written on these pages, and that's because for whatever reason I didn't actually create the pages worth of problems. So we're just going to do this freehand for the most part here, at least for a little while. Okay, so now let's say that we've got, we'll just say that that's 0. We're going to say that at x1 we have mass 1. We're going to say out here at x2, we've got mass 2. And then someplace in between, we've got this thing which is called x bar. And that's because there's basically a line bar on top of it. What is this x bar? X bar is what is known as the center of mass. Also known as the centroid. Kind of a cool name, centroid. But it is the center of mass. So X with the bar over top of it is what is known as the center of mass. All right, and we'll talk a little bit more about exactly what center of mass actually means. But first of all, how would I solve for this? How would I get the center of mass? How would I get that place in the middle, which is known as the absolute center of these two masses? Kind of the balancing point. Well, we're going to go back to what we said before, that M1 D1, oops, not DI, is going to equal M2 D2. Now, what are these distances? The D1 is the distance from the center of mass, or the fulcrum point, out to X1, where the first mass is. So I'm going to have mass 1 times the distance of 1, which again is x bar minus x sub 1. That's the distance from x bar, or the center of mass, out to x1. Likewise, on the right side, distance 2 Now remember, you always take the final distance minus the initial. So in this case, it would be x2 minus x bar, basically working backwards, right to left. So you're always going to take the right distance, which is more the final distance minus the initial. All right, a little bit of distribution here. Now we're just going to do some algebra. M1 x bar minus M1 x1 equals M2 x2 minus M2 x bar. Ultimately, we are trying to find a way to solve for x bar. So let's get all the terms with x bar, and I'm going to put them on the left. So I'm going to add M2 x bar to the left. Meanwhile, I'm also going to add M1 x1 to the right. So we're going to get M1 x bar plus M2 x bar equals M1 x1 plus M2 x2. And then I'm going to do this next part in one step. I'm going to factor the x bar out of the left and then divide by what's left over, which in parentheses would just be M1 plus M2. So what I get is x bar equals M1 x1 plus M2 x2 over, oops, not x bar, I'm solving for that, M1 plus M2. And while that is really the formula, if you think about it, M1 plus M2 is really just the total of all the masses that you have sitting on this piece, on this whatever it is, on this surface. So we call M1 plus M2 the total mass. We just call it M. So really what we get is M1 x1 plus M2 x2 over M, where again, M represents the total mass. Okay, hopefully that makes sense. Now let's give a little bit better definition to what the M1 x1 actually is. Excuse me. M1 x1 is what is actually called the moment of x1. What does that mean? What's a moment of x1? Well, really what it means is this is the tendency, see if I can spell this right, tendency, I'm not sure, tendency for M1 to act as a force. So it's the tendency for that specific mass to act as some kind of a force on our surface. Likewise, M2 x2 would be the moment of x2. And I'm not going to write it, but it's the tendency for M2 to act as a force. So it's the same idea. Tendency for M2 to act as a force. So if you think about it, if you can find that balancing point between the moments of x1 and the moments of x2, then the tendency for those forces to act upon each other would cancel each other out and it would balance. So again, hopefully that makes some kind of sense. If you've had physics already, then this probably is kind of a review for you, but if you haven't had physics already, it's kind of a good introduction. All right. So let's go ahead and define this even just a little bit more before we get to our first real example. So here is our, again, this is going to be our surface of some kind, whatever this thing is, and I just made it as simple looking as I possibly could there. So all along this surface, we've got different masses. So I've got maybe a mass here, 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 and then I've got one way out here. So we'll call this mass 1, mass 2, 3, 4, 5, all the way up until we get to the nth mass. We have masses in between, I just didn't write them all out. And at some point, once again, you will have a fulcrum or a place where the center of mass would be located, because it would, because it would balance the entire thing. And that's where the center of mass would be located. And then you've got your location of your M2, M1, M4, M5, all the way out to Mn. And we know from the definition that we came up with on the other page that x bar is the sum of all of those masses times their x locations. So let's write that, because we don't want to write out m1 x1 plus m2 x2 plus m3 x3 all the way up to the nth one, especially if we were to have a really large amount of them. So let's condense that into a summation notation. So basically, we're going to say we're going to have the sum of all of our masses times our x values. Got to give a little sub I there so we have a counter, where I is going to go from 1 all the way up to the nth one. And then we're going to take all of those to find the center of mass and divide by the total mass, which is just adding up all the different masses. So that's an easier formula probably to use, especially if you start getting a large number of different masses that you have to add up. But it says the same thing. The top part really just says add up all the m's times x's and then divide the whole thing by your total mass. And that's going to give you your center of mass. This, of course, again, this would be if it was a one-dimensional, only x direction. We will get to multi-dimensional later. So let's do a really quick example just to show how easy of a process this really is, especially algebraically. So first example. So we've got our, again, we'll just say that's more of a one-dimensional surface for lack of drawing it in a better way. I could have done another oval thing. I just decided to do this one's a rectangle. I don't know why. So we've got some kind of a mass up here, and we'll say that that's at 2 for the x value. We've got some kind of a mass over here. We'll say that that's at 4, so you'd have a 3 here. And you get a 5. And you get a 6. And we'll say we've got some kind of a mass out here. Notice that I made that a much bigger dot to indicate that that's a bigger mass. So I've got the location. The masses are located at 2, 4, and 6. I need to know what those masses are. So I'm going to give you the mass. The mass 1 here is going to be 5. So whatever we're going to say this is, the mass is 5. Our second mass is going to be 3. And our third mass, because it's much bigger than the other ones, is 11. Using our formula, we can now easily figure out where the center of mass is, where we would place the fulcrum to balance this thing. And if you're looking at it without actually doing the math, I've got a much heavier mass on the right side of this thing. And I've got 2 other masses towards the left-hand side of this thing. So the balancing point you should expect to be someplace probably in between mass 2 and mass 3. And because the masses on the left are a little bit lighter in total than the masses on the mass on the right is, you would think that the fulcrum would probably be a little bit closer to mass 2 than it is to mass 3, but I'm not sure. So we could take a guess, maybe that the fulcrum would be like, I don't know, right here. Looks like that might be a good guess that you could put your fulcrum. Let's see how close we actually are to this thing. All right, so to find x bar, it is mass 1 times x1. So that's going to be 5 times 2 plus mass 2, which is 3, times x2, which is 4, plus mass 3, which is 11, times x3, which is 6, and then we have to divide that by the sum of the masses, which in this case is 8 plus 11 is 19. So let's see what we get. So we get 10 plus 12 is 22, plus 66 is 88, so we get 88 19ths. Let's see, 19 goes into 88 4 times. with a remainder of, what is that, 4 times 19 is 76, so a remainder of 12 19ths, I think, would be left over. So 4 and 12 19ths. It's a little bigger than 4.5. I was close. I think I was a little too far to the right. I'm almost at 5 with my guess, but it looks like the actual fulcrum would be closer to about here. So my guess wasn't that bad. Anyway, so there's the general idea. All right, so let's move on. Let's do one more really quick example. I'm not even going to do mostly the drawing here. I'm just going to draw the number line here. And we're going to say that x is -2, x is 0, x is 6. And let's see, at 6 mass would be 3. At 0, the mass is 2. And at -2, the mass is 5. So find the center of mass. So if you want to pause it and take just a second to do that, by all means, go ahead and do so. All right, if you paused it, hopefully this is what you came up with. So you would have 5 times -2 plus 2 times 0 plus 3 times 6. That is a 6, divided by the total mass, which in this case is 10. So you're going to get -10 plus 18, which is 8 over 10, or 4/5. So your center of mass would be a little bit just past the 0, not quite 1. Okay. Now let's move this into 2 dimensions. As a matter of fact, we'll come back with a second video and do this in 2 dimensions.